So here we want to develop and see a KNN algorithm, classification example in Scikit-Learn. The dataset that we're going to work with is a very popular dataset in Scikit-Learn that it's very popular in between the statistics community as well as the machine learning community. The dataset is actually related to a plant, a flower, and you want to make a prediction, a classification prediction based on a specification of these plants, and specifically two major attributes. If you see in this picture right here, we have the sepal, which is the green part of the plant, and we have the petal, which is the flower part. So we're going to work with the length and the width of these two variables for the data to make a prediction on the type of the plant or flower. The data set is called the iris data set. And as we said, we have four attributes: the sepal width, the width of the sepal, and the length of the sepal, and the width and the length of the petal or the flower part. And these two or these four attributes are very specific to plants. That's why we can actually use them, and we try to use them to make prediction or classification on what type of plant or flowers they belong to. So we have three classes or categories here. We have the first class is the iris setosa, the second class is iris versicolor, and the third class is iris virginica. To do this example, we would do these following steps. And so first thing that you need to do is to download actually the IPython files, and specifically the template file, and open the template file and follow along and code with me. And these are the steps that we're going to do. We're going to import libraries and reading the iris dataset, and then we're going to do some pre-processing and scaling of our data, and also the other steps for model development, which is data splitting and model development and training and prediction finally. Start with importing the libraries that we need. I'm going to import NumPy as MP and import pandas. And also for visualization, we're going to import matplotlib. Right. Next, we need to import the dataset. The dataset is stored and available in the University of California, Irvine. I have left out for you the URL address. So now we're going to actually read the dataset and store it in a variable called dataset. You can call it whatever you want. I'm going to call it dataset, and then I'm going to use the pandas read CSV command. Then I'm going to give it the address, the URL address. Okay, so if you print out the heads of this data now, dataset head. Okay, so we got the first 5 observation or data points of sample. As you see here, it doesn't have actually the headings of the data. So the headings of the data is missing, the name of the variables and features. So that's why we need to actually define it before we import it. So I'm going to define it here. I'm going to define a tuple names, and then I'm going to give it the data that we have. So the first actually feature here is the sepal that is missing from the data, is sepal length, and the next one is sepal width, and next is the petal length, and next is petal width. And the last one is the class. I'm going to use capital C here. The class is the category or the name of the plants, or this is our target variable, right? So now that I did that here, when I read this data set, I'm going to ask the read CSV command to read this data with this new heading or names. So names equal to names. The same names is actually these names here. I can call it actually my name. My names. And then I'm going to put here my names. Okay. So now if you print out the heading here, as you see here, it's printed out with the heading that we needed. Okay. So the 5 observations that we have, the first column is the first feature, which is the sepal length, then the sepal width, the petal length and petal width, and the last one is the class, which have 3 categories or 3 types of plants. We have the Setosa and etc. and Virginica, etc. etc. So let's here do the pre-processing step. So now that we read our data into and store it in dataset, so we have access to it, we need to move on with the next steps. Data is splitting the data into training and data, and then testing, and then training our algorithm, and then making prediction. So, but before that, let's do some pre-processing step here, because right now our data all are in the dataset variable. So before we move on to splitting our data into training and test set, we need to specify the feature variables or X and the target variable or Y. So let's do that. And to do that, there are 2 ways I'm going to show you how to do that. One of them is actually to specify the features. So features, I'm just going to make a tuple of the names of features that we have here. The 4 names here, sepal length, sepal width, petal length, and petal width. So I'm going to make all of these. Sepal length, sepal width, petal length, and petal width. Okay. So these are the name of our features. Now I can specify our independent variable or feature variables and the target variable. So X is going to be the name of the data set, and I'm going to specify that use these feature columns and put them in X here. And for Y, it's just going to be the data set last column here, which is class. So I'm going to say, put the class here. We could also do this instead. We could say, okay, put the data set class. Both of these actually would work. Right, so I'm going to comment this out, and then I'm going to run it. Right, so now if we get, for example, X head, as you see here, we had the first 5 of these, and for Y, we can also do the same. Right, so we have the data. Now we split our data into independent and dependent variables. Another way that we could do this is like this. It would be X equal to our data set. If you look here, the first 4 columns are the features and the last column is class. So this is how we could actually do. Use the iloc, and then all of the rows or all of the samples, and also the only first features, the 4 features. And if you didn't know that you have how many features you have, you could just use -1 up to -1, because the last column, you know that it's actually the Y variable, right? So this would actually put all the samples or all the rows and the first 4 column, or except for the last column, which is the class column, and put all of the data into X variables. And for Y, we could ask it to put use the iLock every data points and the last column 4. So this would also work the same. And now let's see the head of this. Right, so it works. Also, we could do this -1. So there are a lot of ways that you can do this, right? And all of them would work. As we learned before, certain algorithms are susceptible to F-scaling. That means that they need to have the features to be scaled. Otherwise, they're going to be impacted, especially if you have different features with different scaling of data. This is especially true also for the KNN algorithm because it's worked with distance or similarity, how you define it. So you have different features here, the lengths, the widths. Some of them may be longer or larger value, so we need to scale them. It's usually a good practice to scale the features in your data so that it would make the features equally or fairly count in your prediction and training. So let's do that. I'm going to use the standard scale, which is the z-score that we have. We already learned about how to apply and experience how to work with the max-min scaler. So here we're going to use the standard scaler, which is the same as the z-score. So first we need to import it. So I'm going to import it from the Scikit-Learn preprocessing. Its name is a standard scaler. S is capital in both standard and scaler. Then I'm going to make a copy of my own scaler. I'm going to call it my scaler. And this is going to be a copy of the standard scaler. Okay. Now I'm going to feed the training data into my scaler, feed my scaler to my training data, only the features variable. So you have to make sure that we're only going to scale our feature variable. We're never going to touch or scale our target variable. So we're going to feed the scaler into training feature variable and use that to transform the feature variable in training and both testing to transform them. Okay, so let's do that. I'm gonna first fit my scalar to my training independent variable, feature variable, and then I'm going to xtrain scaled. I'm gonna put it in xtrain scaled. I'm gonna call my model my scalar to transform the xtrain. Scalar, right? This is right. My scalar. All right, now it works. We could also do it here. We could use instead a fit transform instead. Transform. So we would actually get rid of this. We could get rid of this and put it here. So we could combine these two lines into just one line. And it works fine. And we're going to do this also for testing. Xtrain scale. I'm going to make this actually all small. Right. And X here, X test scaled. And this is equal to transform. So we do not feed the scalar on the test data. We only want to transform it. All right, so this step is also done. All right, so now that we have splitted our data into training and testing, and also we normalize and scale our training and testing data set, the feature variables. It's time to go ahead and develop our model. So first we need to import the classifier. So I'm going to, from Scikit-Learn, it's in the neighbors module. It has an S, neighbors, import. The name of the algorithm is kneighbors classifier, as you see here. Kneighbors classifier. Make sure that you have the correct spelling. We can actually make it a nickname to make it easier when we want to call it. All right, so now I'm going to create my own model, a copy of this, and it's going to be a KNN. And in the parentheses, we can specify the value for the number of neighbors, K. So the number of neighbors equal to 5. I'm going to go with 5. That's a typical value for KNN algorithm, but it is a very important parameter, as we said before. So it's very important to actually find or tune this parameter, as they say, tune this parameter, find the best value for it. And if you also remember, one of the steps of developing a machine learning algorithm, especially for supervised learning, that we have parameters for the models, some of the models, we need to optimize the value of these parameters. Okay, so later on we're going to play with this to see how we can find the best value to optimize the behavior or the accuracy of our prediction using this model. All right, so now let's train our data, train our algorithm. Okay, so I'm going to use my model, then say fit to our training data set. For the feature variable xtrain, we need to use the scaled one, and we do not and did not scale the train, the y variable or the dependent target variable, so that's going to be itself by train. Now our model is actually tuned or trained, and it's ready to make a prediction. So let's go ahead and make a prediction here. I'm going to call our prediction yPredict, and then I'm going to call my model, my KNN, to make a prediction on the test data, x test, and I'm going to give it the scale data. All right, x test is scaled. Okay, the name of the model was probably wrong. My KNN. Yes, so it works now. Right. So we made our prediction. Now it's time to learn what was, or estimate the accuracy of the model. What was the accuracy of our prediction? So let's go ahead and see what is it. So this is not a regression model. We cannot use the R-square. There is a module in Scikit-Learn, its metrics, that it has all the metrics, the accuracy metrics for evaluating the accuracy of a model. So here we're going to use the accuracy score from that module. So first we need to import it from Scikit-Learn, the metrics module, import accuracy score, and then I'm going to print out the accuracy of our prediction. Then I'm going to give it the accuracy score. The first thing that we need to give it is the actual data, so I'm going to give it the y test. We do not have y test scale. We do not and did not scale our target variable. We never do, right? And then our prediction, y predict. So the accuracy is 100%. That's 100% accuracy, which is amazing, right? Right, so we developed our model, and we made a prediction on the test data set, and we print out the accuracy. The accuracy is 100%, which is ideal. And I can tell you in advance before you go ahead someday in your job and probably apply a machine learning algorithm or classification on your data, on real data in practice, you will never get 100% accuracy. That's like a dream. But that's not the point. The point that I want to make is about the parameter number of neighbors here. We set it up already as 5, just randomly, we set it as 5. But in real world application, you need to figure this out, what value you should use, what is the best value. So this is by itself is actually a step. If you remember in one of the steps in the 3 steps in machine learning algorithm development was optimization. That's optimizing the parameter value to control the behavior or optimize the behavior or accuracy of your model. So this is what we want to do. Our accuracy is already 100%, so I'm not doing this because of the sake of this. I'm doing this because I want to show you how we can actually do this. I'm going to call this optimizing parameter, then finding the best value. So I'm going to create multiple models here with different values for k, and then I'm going to find their error, and I'm going to append them on this error empty list here. So I'm going to use a for loop for I in range 1 and 40. Why 40? It doesn't have to be 40. You can go as long as much as the size of your training data. And so let's do this. So we have 150 data points here. Let me show you here. Data set, shape. So as you see here, we have 5 columns and 150 rows. That means that we have the total of 150 data points here. We use the 20% for testing, so that means there is 80% for training. So that means that we have about 30. We have 30 for test and 120 for training. So you can actually do, instead of 40, go with 120. For I in range 120, 1 and 120, do these steps. Create a model with the parameter number of neighbors to be equal to I, and then we have to train our algorithm using the train data and the scaled one and y train, and then we have to make a prediction. I'm going to put it in the y predict index I. I'm going to ask my model to make a prediction on the test data, and I have to use the scaled one. And I'm going to find the error here. So I'm going to find and append the error here, and I'm going to use the numpy's mean function. And I'm going to say, okay, for all the prediction that this makes for the test data that are not correct, find the average of how many percentage the error is. Okay, so that's going to be y, then y predict I is not equal to the actual value, which is y test. Find the average, the percentage, and put it in the error for the ICE model. Okay. All right, so we are done here. Now we can go ahead and plot it. So we want to plot the error to visualize it. To make it easier, just by eyeballing to see which K is better or which model is better. So let's do that. I'm going to plot this. Specify the plot, the size first, plot, figure, and then the figure size. I want it to be 12 and 6, the width and the depth. And then I want to specify the color and the line style and the marker. So plt plot range 1 and 120 for my model. I want to show the error here, and the color I want it to be red, for example, and the line style I want it to be dashed, and I want to use the marker little circles, marker equal to the little circle, which is O. Aside, all right, and also let's also specify the color for the marker and the size of the marker. So the marker face color. That makes it green, and the size of it I want to be marker size. I want it to be 10, for example. All right, so let's also specify the title of the plot. Title, I want it to be error. The error rates, for example, for different k values, the error rates for different k values. And also we have to specify the labels for the both axes, the x-axis and y-axis. The PLT, the X label, I want it to be a label. I want it to be my k values. And the y-axis, y label, I want that to be the mean error. Okay, so now I'm going to ask to show the plot. There's some problem here. Let me see. Figure size is a problem here. Okay, figure size. Yeah, so let's try fig size. Fig size. All right, it works. All right, so as you see here, we have the y-axis shows the mean error here. The x-axis is the k values from 0 to 120, the size of our, from 1 actually, from 1 to 120, the size of our dataset, the training dataset. As you see here, going from left to right, increasing the k values actually, on average, increases the mean error. That means that it decreases your model accuracy. And the best values, it seems to be like around here values, the value around here. If you actually look closer, we could actually make this evident. The value that they picked arbitrarily, quote unquote, would actually fall between the smaller size. It would fall in this ideal place, the optimal values here. And that's a good value. That's why we got 100% accuracy. And I see here, this is 100% accuracy. There's almost 0% error here for these values. And as we go upper, for about range of 120, 118, 119, the accuracy, the error rate is about 80%. So this is how we would optimize and find the best value for our parameter.